All right. So if you have any questions, you can add them in the chat or in the as a comment, and I'll try to answer them. There's no moderators or anyone, so I'd have to look at it myself. So that will take some time. But yeah. Okay. So let me go to page 2, so that if you've got your handout, you can follow through as well. Right. So let's see. Okay, so one of the things that many of us, it's very simple, is dealing with forms of and formats of time, right? There's different forms of time. Sometimes your answer requires you to give time in a certain format. Sometimes there's a standard form, right? Standard set of units. Sometimes the question, some of the information provided gives you time in different manners. So you should be comfortable with dealing with them. Now, this is one of the common things that many people confuse, many students confuse. So yeah. So yeah, if you got your handout, see if you can try the first question here. It's pretty straightforward, actually. So I believe flew by plane from Dubai to Rome. The flight time was 6 hours 42 minutes. Okay, hours, minutes. That's one form. And the average speed of the plane was 650 kilometers per hour, right? So they're dealing with kilometers per hour. So, right, you want your time in that format, right? Obviously, they're asking for average speed. So average speed, you know what that is? The distance divided by the time. Well, okay, so that's average speed, but what you're looking for is the distance. So distance is going to be speed times time, right? All right, so right, speed is pretty straightforward, 650 kilometers per hour. You need your time, you need to convert that into hours. How do you do that? Now, one of the common errors is by less capable students, I would say, is 6.42 to put that as a conversion, which is not quite right. You could go ahead and do the conversion with the help of a calculator, but you sort of want to know in certain questions how to do the conversion, where the steps are useful, right? So you could do 6 hours, 6 full hours, and then write it as a mixed number, which is 42 minutes out of 60. Why 60? Because that's one complete hour. So this is a fraction of an hour, and there's 6 full hours. So that's one way you can represent this in hours. 6 hours and 42 out of 60, right? So that's that. And of course, you can, from here onwards, you can deal with this, right? You could either convert it to an improper fraction, anything you want. So we'll work with this. 6 times 42 over 60. We could also simplify this and say, okay, 6 times 7, 6 times 10, 65. And yeah, so it'll be what? 65 times, so converting this into an improper fraction would be okay, so yeah, we can't really do that, so that's my bad. So let's see, 7 out of 10, and yeah, so then you can convert this into 67 over 10 times 650, divide that, multiply that, and you should get your answer, right? Which is 67 times 4,355, is it? Yeah, 4,355 kilometers, right? Assuming I didn't make any errors there. That's not the main point, not the simplification, but the idea of converting, right? All right. So Next. So here's some exercises, 1 hour and 15 minutes. How do we do that? Same as we did here. We could do 1 hour, 15 out of 60. If you could also write it as simplified. So 1.25 hours, right? Or you could go to decimals and say 1.25 hours, right? Because 1/4 is 0.25, right? Then you got a mixed number in hours, which is something we already did. So first we would convert that into decimal. So it'll be 3.4, right? 3.4, which is hours. And then you multiply that by 60, which will give you the number of minutes, right? Which would be 204, right? 204 minutes. Next, 7.3 hours. Now, this is a classic error as well. So how do you split this up? You would do 7 hours, 30 minutes. Well, that's generally what students tend to do. But then you should know, okay, 7.3, how do we think about that? 7 and 3/10, right? That's the improper fraction. Let me actually bring that over here. 7 and 3/10. That's the value. So you would convert that into an improper fraction, which would be 73/10, which is 7.3. Oops, no. We're going to convert it into minutes. So that's 73/10. Multiply that by 60, right? And yes, that should give you what you want. 73 into 6. Once again, 204 minutes, or you could even say 7 hours and 3/10, which is 18 minutes, right? Let me recap that. So it's basically 3/10, which is what 0.3 is. And that converted into minutes, you would multiply that by 60, right? Which will give you 18 minutes, right? Right, so that's about time. So make sure you know how to work with these formats, how to interchange between the two, and so on. Page 3. Let me see if we've got any comments. No, all good. All right, so again, simplifying algebraic fractions, one of the areas where students tend to struggle, especially algebraic simplification. Here's 4 options, A, B, C, and D. Could you identify the error, right? So A, one of the things the student has done is correctly understand that they have to divide both the terms, right, in the numerator. So 9 divided by 3 is 3. 4/3, they've actually rounded it, right? Because it's a recurring, so they can't really write it, right? So they've rounded it to 1.3, right? Now that's the blunder there, right? So that's an error, so you can't really do that, and you want to follow through with the fraction itself, because otherwise you're going to get to the wrong answer, right? The accuracy is going to be lost, right? Part B, what do you think is the error there? So this, again, classic error. Student has gone to multiply by 3, which would be generally a good practice when you have algebraic fractions to get rid of the denominator. But in this case, student has ignored brackets and understanding that they have to multiply both sides by 3. So when you say sides, it's not just 7. On your right-hand side, you've got 7 and minus 2m, 2 terms. So when you say multiply the right-hand side or both sides by 3, make sure you know what you're doing. Multiply every term that's on that side, right? So I think this should have been minus 6m instead of minus 2m, right? Which was the blunder there. Let's look at C again. This time, unlike student A, this student has thought, okay, I see a common factor. Let me just cut that out. 3 times 1, 3 times 3, and then simplify it. Here too, the denominator 3 belongs to the entire numerator. So this really means, 4m plus n divided by 3 really means that the entire numerator is being divided by 3, not just 9, right? So so if you wanted to break it down correctly, you would break it down as 4m over 3 plus 9 over 3, which is 3. So it'll be two different terms, both being divided by 3, which is the error this student made, right? So make sure you don't do that. Right? Now this looks pretty good. The first step looks identical, dividing by 3. The next one is where the error happens. Multiplying by 3 both sides. Now it looks like we multiplied both of them by 3. So that seems to work out. But could you identify what was missed out here? So here, technically you're multiplying both sides by 3, right? That's how we make sure an equation is consistent. So when you multiply by 3, 4m over 3 plus 3, that side multiplied by 3, and also the other side multiplied by 3, right? Both sides, right? So this gets multiplied, becomes 4m, just like we expected, but also this gets multiplied by 3. So it becomes 921 minus 6m, right? And then you can take it as follow through and simplify, right? Okay, which gives you m equals 1.2, right? So A, B, C, D, all are different variants of errors you may have done in some part of your practice papers. Maybe because you were in a hurry, maybe you didn't know, maybe you're confused, right? But the general accepted method is to first get rid of the denominator by multiplying, right? And then follow through, right? Make sure you multiply both sides, right? Yes. So let's go to page 4. Yeah, so here's your examiner comment. Candidates must be reminded to multiply the whole side of the side or the contents of brackets by the numerator of the other side in an equation of this type. Right, so have that in mind when you're solving algebraic fractions, right? Let's go to page 5. All right, so take a moment here if you're watching. See if you can spot what the error is here. This one, I would say it's a little more challenging, right, for many students, but see if you can spot what the error is that this student has made. Now, I'll tell you one thing. It's nothing to do with the calculation, right? The calculation side, the student has applied the definition of area properly. Simplification is good. And the argument seems right as well. But what do you think the student missed out on? Okay, so we'll try this. So we'll say we've got a hollow cuboid. All right. And they've given the dimensions. So I'll say that's 12 centimeters, 4 centimeters, 3 centimeters, 3.0. Now, it seems like what you should do is find the surface area, right? And see if 110 exceeds that or is less than that. Seems like very simple. But notice this. Each length is given to two significant figures. So this is not the accurate, the precise value of the lengths and the dimensions. It could be, so rounded to two significant figures, 12 could be, so 12 second significant figure 1. So it could be the upper bound could be 12.5. And the lower bound could be 11.5, right? Upper bound, lower bound. That could be the lowest value and the highest value. Same thing for 4. It's rounded to 2SF, which is the first decimal place, the second significant figure. So yeah, 0.1 divided by 2, 0.05. So it could be 4.05 or 3.95, upper bound, lower bound, right? Same thing with 3, you would go 3 point, 3.05, 2.95. Okay, so this question, notice, now this might get a little easier for those who are, who understood what the question refers to. But this question, watch how it never mentions anything to do with upper bounds, lower bounds, right? The only giveaway is this part, the idea that the dimensions are not exact values, but they are rounded to a certain accuracy. So that should be one of the giveaways. For more higher tier questions, you should spot these things and then figure things out. Okay, so determine if this tin of paint is definitely enough to cover the 6 outside faces of the closed box. Now the next question is, do you go for the upper bounds of the surface area or the lower bounds, right? So the surface area would be, so I'll use this. So what do you use? First question, do you use upper bound or lower bound? So you want to know if the amount of tin, tin of paint, is that going to be sufficient to cover the entire cuboid? So for that, you would consider the largest possible box, right? Because that could be the worst case scenario, right? Largest possible, and see if it works, if the tin of paint is sufficient, right? You wouldn't go for the smallest lower bound of the surface area, because if the box turns out to be a larger value than that, right, bigger than that, then you're going to run out of paint. So you can't really use the word definitely enough in that case. So you want to push for the worst case scenario, right? Okay, so then you would go for your upper bounds on all of these. So it'd be 4.05, 3.05, 12.5, 3.05, 12.5, 4.05. And turns out, when you do this, the calculation turns out that the surface area of the cuboid, the largest possible cuboid, is larger than the amount of tin by a little bit, so 202, something like that. So it's not definitely sufficient, right? You couldn't say it's 100% enough, right? It could be, but can't say definitely. So here's a question to watch out for, where they haven't specifically mentioned the idea of bounds. May seem straightforward like this, but it's not. There's something hidden behind that, right? All right, let's have a look at the chat. Okay. Right, so here's another question, pretty similar. How are we going to do this? Peter transports metal bars in his van. The van has a safety notice, maximum load 1,200 kilograms. Each metal bar has a label, weight 60 kilograms, right? For safety reasons, Peter assumes that 1,200 is rounded to 2SF and 60 is rounded correct to 1SF. Calculate the greatest number of bars that Peter can safely put into the van if his assumptions are correct, right? Again, see, seems pretty straightforward. Like if you really ignore this part over here, it's like, okay, maximum load 1,200. Each bar is 60 kilograms. Let me just see how many of these can I fit, right? So 1,200, that's how much it can carry. Each one is 60. So you should technically be able to carry 20 bars safely. Seems too easy, really. But again, the giveaway being these values are assumed to be rounded, not exact values. So technically 1200 could be, the 2SF would be the hundreds place. So 50 you could add and subtract. And there we go. So those are your upper bounds and lower bounds for the maximum load, right? And the weight could be anything from first significant figure was the tens, so 75 kilograms, oh actually 65 kilograms, and 55 kilograms. Right. So now things change, the picture changes, right? So what are you going to assume for the maximum load and the weight of the bar? You want to assume safety first, obviously. Wants to be safe. So you're gonna, you're not gonna try and optimize. You're gonna think about the worst case, and try to see if it's secure, right? So the worst case meaning maximum load. What do you think? I would assume that's 1,150 kilograms I can hold, because I feel like, okay, it's not going to be able to do 1,250. I'm going to assume the worst case. That's the worst case for the maximum load. My van can only support this much, right? And then the weight of each bar, 60 kilograms. What do I assume? Well, I'm going to assume that it's much heavier than that. What if it turns out to be heavier, right? Which is the worst case scenario, right? So now you could sort of divide and figure out how many bars you could carry. So that'll be 17.69 if I've done the calculation right. 17.69. So now again, something else to do for us. Do we round up? Do we round down? Do we say 18 bars? Or do we say 17 bars? Seems like if you were to round it, it'll be 18. But the actual answer is 17, because 17 was the limit, the number of bars you can carry. You don't want to overshoot that, right? That's a risk, right? You want to stay under that. So even though it says maximum, greatest, right? You want to always be under this amount, right? 17.69. And you can even say 17.69, because that cannot be the number of bars. So you have to round it to an integer, but 17 would be the accurate one. All right. Here again, something very similar to question on page 5. Bounds not directly evident, but watch out, right? Based on the dimensions, on the accuracy they've given to, right? Page 7. Let me take a break here. Let's see. All right. All right. Well, here's another question that was very interesting. I would like you to give this one a try. Right? Well, actually, I want to modify this, to be honest, right? Let me remove this, right? And let's say this is 28.3. So I'm going to make a small change in this question, right? I actually did this with one of my students, right? And the results were interesting, right? And changing this number a little bit, and the question was asking for, let me see. What's the question asking us? Yes. Let me add that. So this shouldn't be in your handout. I think this is something I sort of stumbled upon. Let's see. Write down the lower bound for the length of. Okay. Length of BC. So note I've sort of got rid of. Let me wipe that out. That. And now I'm sort of giving you what AC is. And I want to find the lower bound for the length of BC, right? And let's say 28.3 centimeters for AC is rounded to 3SF. 3SF. So it's correct to 3SF. This length over here is correct to 3SF, right? Take a moment, see if you can figure this out. In the meanwhile, I'll sort of add what the student did, which is very interesting. So let's have a look. Let's see. All right, there we go. So I'm going to add. Okay. All right, here we go. So basically, most of you all would understand that the Pythagoras theorem is what comes into play in order to find BC, a right angle triangle with the hypotenuse and one of the legs being given. Okay, so I think the students successfully identified the upper bounds and lower bounds, right? Which is, so, well, okay. So the upper bound would be 25, lower bound would be 15, right, to 1SF. This one, it is 28.35 and then 28.25, right? Now, if you notice, the student has applied the Pythagoras theorem correctly to make BC the subject, but here's where things kind of gets interesting. So, and since it says lower bound, of course, like many of us would, he's plugged in the lower bounds for the different dimensions, A, B, and AC, right? What are your thoughts about that, right? And they got 23.9, right? But the student, in all of these square roots and squares, hidden was this operation was a subtraction. The operation behind that was subtraction. And when it comes to a subtraction like this, I'll tell you, many of us who are watching would kind of know already that it's always, if you want the lower bound, it's lower bound minus upper bound. But since this subtraction is sort of hidden within the square root and the squares, people tend to miss out on that. So here, yes, the lower bound on the first value, AC, but then you want to subtract by a larger value because you're getting a lower bound. So here it should have been 25, and the student actually eventually caught up to that. And yes, the answer, the lower bound, actual lower bound of that length is 13.2, right? So in this question, yes, it directly said bounds, watch out for bounds, but the operations are equally important. What are you doing? Division, addition, multiplication, subtraction, and you want to pay attention to that when you're deciding what you want to use, right? Not just because most of us would say lower bound and then pick lower bounds and plug it in, right? That doesn't work all the time. So something to watch out for, right? All right. Let's see. Okay. Another one is recurring dot terminology, right? This one, I think more capable students wouldn't have much problem with, but then again, from time to time, I sort of see this coming up as well. And so, okay, just to introduce you to what this is, so this one, what's the error the student made here? Well, this doesn't mean that 2 is repeating. Just 5, 4 is the one that's the repeating unit. 5, 4, 5, 4, 5, 4. Right? That's what's repeating. Right? So here's an exercise. So if you look at each of these, 0.707, it's about identifying what's the repeating unit. Right? What's the smallest group that repeats? So here it's of course 70, 70, 70, 70. So 0.70, you would draw that, right? 2 of those repeating is the dot notation. Then let's go for the next one, 0.50. So after this, doesn't seem anything's recurring, but then 8 seems to repeat. So you would do 0.508, and then that's the one that's repeating the digit, right? Next, this is also good. So let's say you want to say, how do we write this? The student that what they wrote, 0.254, 254, and so on. How would this look like in dot notation? Okay. So if you want to do this, you don't really do this and say that all 3 are repeating. We don't tend to do that. That's not the correct terminology, although it would make sense. But 0.254, you would just, go for the 2 extremes digits and then include that. So that would indicate this. Everything in between them is repeating. Right? So you would go for the end digits, the first, the last digit of the repeating unit. So same thing here. So you've got 0.705, 705, 705, so on. And of course here, 0.705, both of them repeating, 05, 05, 05. So yeah, if you're not familiar with it, have a look, revise on recurring decimals. It's not that difficult. It's pretty easy to figure out, right? Page 9. Okay, one of the biggest things that I see with a lot of students, geometry in itself, I would say it's not easy, right? A lot of higher tier questions are based on geometry, I would say. And they're rather challenging. And I would also say it's one of the more easier to solve, right? There's not a lot of things or like there's no algebraic manipulation as such. It's just looking at some properties, recalling certain properties of shapes, and then applying them. So the maths looks simple, but sort of figuring out things is the challenging part in geometry. Okay, this one's a classic one. Assuming it's a right angle. So obviously, I think the examiner comment wraps it up. The candidate incorrectly believed that the triangle was right angled. Candidates will be given an indication of a right angle, usually by a symbol. So if it's a right angle, it'll be very clear that it's a right angle, or written number, or it'll say the number, but sometimes by a statement. Now that happens rarely, right? If it's a right angle, they're not going to try and penalize you by hiding it in the question, right? If it's a right angle, they'll pretty much draw the symbol almost all the time, right? So yeah, so if that's the case, do not assume. Stay away from assuming, right? And yeah, obviously in circle theorems, that's the assumptions is your biggest enemy, right? I would say. Because it's really convenient to sort of assume, and then everything sort of falls into place. And your examiner, the people setting up the exam, sort of know about this. So yeah, it can be misleading, certain diagrams. So watch out. Do not make assumptions. So let's look at this. For example, one of the classic assumptions is the Z shape. This one over here. That's terrible. Many of us, I think, even myself at a younger age, I sort of did this Z shape, watch out for the F shape, and things like that. But then you tend to see you fall into a lot of traps when you think of it that way, right? One of them is this one. You see the Z shape, and very conveniently, you sort of assume, okay, wow, that's 71. And then things become really easy after that. But, you know, you've already blundered. You've made a huge error here by assumption, right? So, yeah, so do not do that, right? In this webinar, I won't really be discussing or walking you through circle theorems. That'll be for another session, hopefully. I've sort of planned that out as well for circle theorems, but this is not the session for it. This is basically giving you some tips, right? Things where people go wrong, right? Right, the next one. Yeah, here to give it an attempt, pause the video if you're watching the recorded video, and see if you can figure this out, right? Okay, so very conveniently, here are a few things that might go wrong. One is to assume this to be the center, right? And then, you know, applying angle at the center is twice the size of the angle at the circumference, which immediately gives you 58 degrees as the answer, which is completely wrong, right? That's one of the big ones. So, okay. Apart from that, what else could go wrong? Okay, let's see. So one might assume now this is a right angle because it looks like one, right? And then they might go, okay, this is 65, sums up to 90. So that angle is available. And then you could go on to find this. Now, on purpose, I've sort of manipulated you to go along this part and get into this big trap. So let's try this. So 116 plus 65, you take that away from 180, right? And what does this give you? So this will be like 281, is it? 281, no, 181, is it? 116, not 165, 65, right? Okay. 65, so it'll be 181, and then you get -1. And that's a dead stop. Now, usually, sometimes that might not be a dead stop for you, but you've already made the error, right, of assuming the right angle. right? The right way to go about this would be to find this because it's angles in a straight line, and then think about this triangle. Angles, the sum of angles in a triangle, right, would give you x. That would be the appropriate way to do it. So yeah, I think so one of the common things to assume is center of circles, big one, that is a Z shape, F shape, all of that assumptions, right angles, and then equal lengths. Sometimes even equal lengths, same thing, right? If it's equal, they'll either specifically mention that they are equal, or they'll, more often than not, they'll sort of indicate that geometrically. Okay? So yeah, there's no reason to assume. If you're going to assume, see if you have evidence, right? Page 11. Okay. Let's have a look at the chat if anyone's in. All right. Show that how many marks did the following candidates get? Show that square root of 45 plus square root of 20 equals 5 root 5. Look at what they've done. This one, again, typically I see a lot of students doing that. Sometimes even in your term test, you are sort of accommodated, right? You sort of get marks for this. So that probably, it's sort of like encouraging, incentivizing students to, use the calculator and then simplify it. Certain schools tend to do it. If your school's one of them, when you're doing your past papers, make sure you follow the marking scheme, follow the examiner comments, see where you end up with your marks, method marks, your answer marks, right? So do you want to guess how much this student got here? The answer is absolutely right. This part looks correct, right? But got 0. Even. So you're not going to even get the answer mark. You're going to get 0, right? All of the work for nothing, right? So what's the step that was missing? Well, pretty simple. You just had to simplify, showing that how does 45? That's 9 times 5, 5 times 4. And then, of course, this step over here. Bring out the square numbers. 2 root 5. That's it, right? So that would have earned you your method marks and then your answer mark, right? So this student got 0. Part B. Okay. Here too, I'm not gonna elaborate on this, but again, this one has to do with rationalization. I think the student has picked up on that idea and identified correctly what to multiply by. But again, steps missing. Probably used the calculator and sort of tried to show that he's got some workings going on, but this is you're not going to get away by trying to show some method, right? You better, if you're doing that, if you feel sketchy about what you're doing, right, calculate and then sort of manipulating your workings based on what your calculator is giving you without really understanding the concepts, then you're probably you're going to have to fix that before the exam. So now's the time. That's the whole purpose of this session, is to highlight some of the errors that you may be doing already, that you don't know that you're doing, and you think you might not know you're losing marks on it. So yeah, that's why this session is all about. So fix that. In this session, I won't teach you anything, but I'll just highlight these things. So yeah. Page 12. Once again, okay. So Converting to improper fractions, that will probably earn a method mark, right? Converting to multiplication, that probably would get you a mark, but then your final answer, right? The final step that they were looking for is, how did you go from here? You seem like you simplified, but how do you go from here to here? Definitely, that seems like the calculator has come into play. That doesn't seem, there's no rational way or evidence as to how you got from here to here. So that's this missing step, right? Which is either you do 35/9, and then you sort of at least show this part over here, right? Okay. Right. So show that questions. In calculator papers, like both your papers are going to be for IGCSE, these questions, you want to really be spot on what steps you need to show that in order to earn all the marks, right? If you are getting away with your calculator in your term tests or in your tuition class, things like that, make sure you know what methods are. Either you ask someone who knows about it, who has thoroughly followed the exam schemes, the examiner reports, marking schemes, or it should be pretty evident in the marking scheme as to what methods they want, right? So yeah, whenever it says show, use algebra to, you must show your working, show full algebraic working. You should be able to look at your workings and sort of from one step to the other know exactly how this flows, right? Shouldn't be like how did I get from here to here? After several days, you look at your question. It shouldn't be like that, right? Page 14. Precise vocabulary. Okay. This one again, among students, mostly who generally English is not their native language, or around Asia, I would say, tend to ignore the exact wordings of the theorems. I don't know if it has to do with the language barrier. I don't think so. I don't think it's that difficult. But I think the way we sort of study maths with these shortcuts, memorizing techniques, little fancy things to, get over things, I think that has to do with why people miss out on these sort of answers, right? So here's one, tangent theorem. No such theorem. There's nothing called tangent theorem, right? Doesn't make sense, right? This one's good. Triangles connected to the center and the sector are isosceles triangles. Well, not exactly, could have been much more simpler, right? You could say OPQ is an isosceles triangle. That should be pretty straightforward, right? If you wanted to add more, well, you don't have to. You can just say OPQ is an isosceles triangle. Here's another one. It is half the angle in the middle. Half the angle in the middle. Two errors here, if you notice, right? If you look closely, one error was the middle has been identified as this being the middle, which is not the middle. That's not the center, right? That's an assumption, right? And half the angle in the middle. What is half the angle in the middle? Like, that's not sufficient at all. So 2 marks, they're looking for 2 keywords. You can think of it like that. One, angle at the center is twice the angle at the circumference. So something along those lines would get you 2 marks, right? So here you go. Many of us, so this student wasn't able to actually solve it, but many of you will be able to solve it, like this, maybe apply the theorem correctly, but then the reasoning. So here's exactly what the examiner comment is. Students often know the practical implication of circle theorems. They don't know how to solve it. They know how it works. They know how to figure it out. They know the shortcuts. They know different things. But lack of precise vocabulary means they often gain no marks for the reasons required. This again, alternate angles instead of alternate segment theorem. You're not going to get away with something like this, right? Students tend to think if my answer sort of has those words a little bit here and there, it's not going to work, right? That's not how it goes. You want to be really precise. Right? You have to really understand what you're saying. It shouldn't just be, you know, you're not just putting it down there for the sake of it, right? Okay. So let's try and fix these. Incorrect reason, Z shape. Well, that's alternate angles. F shape, again, what's that? Well, that's referring to probably this angles when they are parallel lines. So that's corresponding angles. And then angle at the diameter is 90. That's kind of here and there, here nor there. So the correct one would be either you say that angles in a semicircle is 90, or you could say angle subtended by diameter at circumference is 90 degrees. Right? These two would work, something along the lines, right? So it's up to you what you feel confident with. I would go with the simpler one, angles in a semicircle is 90 degrees, but yeah. Right, page 16. Okay, are your answers realistic? Now, usually this, I can't say it helps too much, but this is more of a confidence thing, right? You telling yourself, okay, acknowledging or trusting what you've done, right? Or acknowledging that what you've done is correct, right? So when you look at answers, you sort of know if you get certain answers. By now, I'm sure most of you all, if you're taking your exams in May, right? You kind of know when you get an answer, this doesn't seem right. For example, if you get an ugly answer, right? Like some recurring, some random answer, which is not nice, which is not a whole number, or like a, a simplified version, then you tend to get, skeptical about it, which is good. So, and sometimes when you get a really nice answer, right, a whole number, everything seems to fall in place, then you sort of reinforce yourself and say, okay, seems good. So I like that part of it, reinforcing, right? And in this part, not just because it's ugly, right, but there are certain things that you can watch out for to identify errors. So this is checking your answers if it's realistic. Does it make sense? Is to identify any errors you made, whether you've entered it incorrectly in the calculator, have you made any blunders along the way, right? Or have you made a wrong decision, right? Some of the examples would be, let's say you got probability, probability should be between 0 and 1. Now, if you get something greater than 1, probably you've, added instead of multiplication. So that should give you a tip, right? To go fix it, right? So, but if you ignore the value of your answer and the practicality of it, like the idea that if you're not really thinking, okay, this is a probability, this is the chance of something happening, it really has to be within 0 and 1, that's when it's realistic. That's when you can identify errors. If you're ignorant about it, then that's not good, right? Because it's not like you can always have a perfect calculation. You're bound to make typos, mathematical errors, entering in the calculator, mishaps like that. So these sort of things can help you out. Another one is time cannot be negative. If you get negative time, you've probably entered it wrong in the calculator or something like that. Cannot be negative. Or it just means that you have to ignore that solution, right? And that's an important thing. You do a quadratic in terms of t, and then you get one answer that's negative, one answer that's positive, right? You should be aware that you're working with time, you're dealing with time, and that realistically time can't be negative, and so ignore one of the solutions, right? So that's important. Another one, if when you're working with series and sequences, right, you're dealing with n, right? So if you are blind about the idea of what n is, what n stands for, which is number of terms, right, then it's bad, right? You want to know, okay, n is the number of terms. So when you're solving something involving n, right, you're supposed to get a whole number, right, an integer, right, an integer, positive integer, actually, right, because it's the number of terms. That's when it's realistic. This one too, about an investment. More than this, I think some of the errors with reverse percentage can be avoided, like by understanding, okay, I bought something for some value, and it seems like the person is selling for profit. Okay, that means my answer, what I want at the end, realistically has to be greater, the final price, because I'm making profit. My selling price has to be larger. And then reverse percentages, of course, if you knew someone sold for profit and you knew the selling price, you should know that he started with a lower amount, right? Or if you know what the investment amount was at the end, you should know that he probably deposited a smaller amount at the start, right? So those sort of things, being realistic about it is very useful, helpful, in sort of getting some insight whether you're doing things right, whether you've got to the right place, right? Okay. And what else? There's many more, actually. You could say, so this has to be a positive integer. Scale factors, for example. Another one, scale factor when you're dealing with transformations, right? Or similar shapes. You have to have the idea that a fraction, a value between 0 and 1, right? A scale factor between 0 and 1 is describing a transformation that's shrinking. It's getting smaller, right? You have half the size that you had earlier. So the original and the final, right? The final image has to be shrunk by a certain factor if the scale factor is between 0 and 1, right? Versus if it's greater than 1, right? You should know. So whenever you get your scale factor, match it up with what you see in the diagram or what they have told you information. Does it match up, right? Is your original image larger than your final image, or is it vice versa? So you should be able to relate these things. So scale factor is another one. Because a common error is they're looking for the scale factor going from A to B, right? You can clearly see that the second object or image or shape is larger, but somehow you did your ratios and you obtained, the reciprocal of it, for example, like the reciprocal of the length, like that, which turns out to be a fraction. Then you can sort of adjust if you had in mind that realistically I'm going to get a larger value than 1, right? So yeah, so these are some things, as you try questions, make an effort to think about, is this realistic, right? I can't list down, it's not like I can exhaust all the possibilities of practicalities and then ask you to do this all the time, like check if probability is between 0 and 1. It should be natural to you, right? You should always think about, okay, this is a problem, there's a context to it, especially questions with context, real life context. Work with the question and then put yourself in that situation. Always think about, get yourself into that question, understand it, and then think within the context itself, right? Yeah, that's the advice. Page 17. All right. Amazing. We've got the function g is such that gx equals square root of 19 minus x. Find f of g, f g of 3. Which are the, okay, so this one's referring to part D and understanding the definition of domain. Now, if you're used to this routine of finding domain all the time, this is correct. Everything this person has done, identify the function, square root function, and that 19 minus x has to be greater than 0 or equal to 0. Perfectly fine. Looks good. And then rearranging looks good. Inequalities, understanding that is good. Reversing of sign. Perfect. But then this is the domain, right? This is what x can be, right? X has to be less than or equal to 19. These are the values you want to use, you want to include in your domain. So domain is all about, domain is what inputs, or x doesn't always have to be x, but inputs, what can you input to a function to get a real output, right? If you put x equals 25, that's going to be an error, math error. So that's not part of your domain. That cannot be within your domain. You have to exclude it from your domain. So this is asking x, which values of x cannot be included. So in any domain. So what are the values? These are the ones you should include in your domain. So what shouldn't you include? X greater than 19, you fall in trouble. So this should not be included, right? So I think understanding the question, reading the instructions, it could be several cases. One, it could be you are not aware or you're ignorant about, whenever you say domain, you just have in mind do this with square root functions, do that with rational functions, things like that. That could be one. Either option number two could be you're not sure what this really means, what domain means, or what cannot be included means. The other, you haven't identified the keyword, right? So do not lose marks for those reasons. If you don't know what it means, maybe this helps, but you can dive deeper. There's many resources on domain. Same goes with range, right? All right, the next function, give it a go. Fx equals, this is a rational function. The denominator, of course, cannot be 0. So x cannot be equal to 2. So you want to exclude 2 from domain. Do not use x. So your domain has to be domain. All real values of x, x not equal to 2, or without x, or something along those lines. Without x equals 2, or exclude 2. Right? Or you can use anything for x, match your domain, but do not use x equals 2, right? Do not use x equals 2, right? Right. Okay. Question. All right, another one of my, again, I sort of try these on some of my students, right? And then almost all the time, they sort of fall into that trap, right? And okay, so here I'm going to sort of plug in our website as well. So some of these questions I pick up from older exams. So we've got an archive. Let me share that as well. So let's see. Let's see. So we've got this collection that I've collected some on our website. It's free to access, so you can also access that. Let me share that. Okay. So if you go to our website, cloudlearnx.win, you can go to this old exam papers archive, where I've sort of collected a lot of old exam papers from GCSEs, IGCSEs, specification A, spec B, all of that. And I've started, from 1950s, 60s, 80s. Now, some of those questions are too challenging. Some of those questions um, are really insightful, right? You're not likely to get those questions in that format, right? But whatever you learn from those questions is very useful. And I kind of see those sort of doing a 360. I sort of see those in more recent papers, those sort of ideas coming back. So I would recommend, if you've got the time, try old papers, even 2001, 2009. There's these gems of questions sometimes that sort of sort of tests a deeper understanding of different fundamentals, because sometimes what you get is your recent past papers, you sort of get used to the same type of questions, same things being tested, kind of. But then the old exams, they sort of have really nice questions. Like I said, gems of questions where it tests your fundamentals. So I would recommend, trying some of these questions. Yeah, to improve on your higher tier capabilities on tackling higher advanced questions. Right. All right. Right. Back to sharing that. Okay, so here's one. So I think I've got a screenshot of. So give this a try. So obviously, I've sort of indicated that it's the cosine rule that's being applied to get a relationship in terms of x. Several things that could go wrong. But yeah, here's what happened when I actually tried this out. So, all right, so let me add that to the whiteboard. Okay, there you go. So that's pretty much their workings. Now what they did from here, I'm going to sort of, because they corrected eventually, so corrected it once I pointed out, so I don't have some of the other workings because it sort of was corrected. But what the student did was, okay, wonderful. They did that. So all of these up to this, simplification looks good, right? Expansion, very nice. This is a very capable student, right? And then plus 12x minus 12x cancelled. And then yeah, go about simplifying, right? But that's a big blunder, right? A big error. Now here you could almost excuse the student because it looks horrifying, right? It's looks like looks like a mess. So every opportunity to sort of cancel things out is very pleasing, and very you get lured into it, right? So, but shouldn't be doing that. Should be aware that always it's this part that's separate. That's a separate term in its entirety. This is one term. This is another term. This is another term. You want to completely simplify that, simplify that, simplify that, and then combine them, right? So yeah. So the correct approach of actually doing that would be to actually assume that, well, you could actually simplify cos 60 and say it's half. So it'll be, let's see, I think we have what the student did, so we can just use that. Let's see. Anyways, okay, so supposed to be 2x squared plus 12x plus 36. And then you have, yeah, well, you can simplify all of this. That's fine. And then you have minus 2x squared plus 6x times half. You could either simplify that, or you could, multiply this out and say it's 2x squared plus 12x times half, and then the rest of it, and eventually multiply by half. But yeah, I'm not going to go into detail there, but essentially what happened here, I'll take a simpler problem to show you what the problem is here. So when you have something like 18 squared equals 11 squared plus 13, no, let me actually simplify that. So you have something like this. You do your cosine rule, you get 198 equals 121 plus 45 minus 11 into 7 into cos, let's say, okay, I'll just call this a squared, right? Just for the sake of having an unknown. Cos 60, okay? So you can't just do this part separately. Like you can't combine these things and then multiply by cos 60, right? Remember that this is a separate term. 2bc is separate. So you want to figure out that first, do the multiplication first, and then think about adding, right? So you want to consider this as a separate unit, right? And not like that. That's different. That's a whole different thing. So cosine rule, make sure you are confident in dealing with more complicated questions like this. I think this should be, if you are confident with handling cosine rule, I think this question will sort of either tell you, no, that's not right, or will tell you, yes, you're pretty good at handling cosine rule and simplifying it, right? Yes. Page 19. Okay, here's another one. Algebraic fractions with when subtracting. So the common error is you do your cross multiplication, minus 3 x plus 1. Okay, yeah. And then you do over 6, let's say, equals 5. Okay, and then you take your 6 to the other side. In simplify, you do it like this. Well, okay, so let me actually fix that. So I'm trying to sort of do it incorrectly and spot the error. So 4x minus 2 over 6 minus 3x plus 3 over 6 equals 5. And then get rid of the 6. So it'll be 4x minus 2 minus 3x plus 3 equals 30. Multiply both sides by 6. Already committed the error. What was the error? This minus sign belonged not just to 3x, this entire thing. You're subtracting this entire thing. So it should be plus 3 minus. Right? When you're expanding it, it's minus 3 getting expanded. Right? Or you could do that to say that you're subtracting this entire thing. Use brackets when you're doing the subtraction. Right? Okay. So I'm trying not to give you in detail explanations on how to solve everything. The takeaway from this particular session or this webinar is, okay, here are areas that you may know you are having trouble with. You may not know if you're having trouble with, which is the worst case scenario. Now I'm going to point them up to you. I'm going to put them right in your face. And so then it's up to you to sort of, I'll also give you some guidelines and some resources on how you can fix those things. That's exactly what I'm doing here. I'm putting them in your face and telling you, okay, try doing this, try doing that. But I'm not going to explain everything. That's not the purpose of this webinar. All right, next, translating literal statements in equations. All the way from the simplest questions to the most challenging questions, this can come up in different places. So you really need to get to work on this, right? So let's start with the first one. Alice's average speed. So let's say Alice is A, Morgan is M. How do I build a relationship? 20 miles per hour slower than Morgan. Okay, this is where everyone goes, okay, slower, A minus M equals 20, A plus 20 equals M. How do I do this, right? So, okay, so you start with Alice, 20 miles per hour slower than Morgan. Okay, so Alice has to be slower than Morgan. Okay, that's where you start with. Alice has to be slower than Morgan. So Alice has to be slower, so has to be slower than Morgan. 20 miles slower. How much slower? Why am I subtracting 20? Because Alice is slower than Morgan, right? Well, actually, I did that wrong. That's okay. That's a big... so it can be confusing for the best of us. So there you go. But that's completely wrong. So you say Morgan is this much. Morgan is this much. And you say Alice is this much, right? So Alice has to be slower, right, than Morgan. So if Morgan was 100, Alice has to be 80. That's kind of really nice to use some numbers. So if Morgan was 100, Alice has to be 80. So M minus 20 equals 8. So you can see can be very confusing to come up with that straight away, literal statements into equations. I almost think sometimes it comes to you naturally for some people. I tend to kind of struggle with that. I sort of need to reinforce, use examples and things like that. But yeah, somehow you want to work around it if you find this to be a weakness of yours, right? Now, obviously, this one's a little more challenging. That's why I've picked it. There are more simpler stuff that you might have trouble with. Number 2, twice as many girls go sailing as they go climbing. Now, this is something you might see in a Venn diagram, for example. They might give you a set like that and a rectangle there. And so let's say sailing, climbing, and then you have 5, and 10. Okay, so sailing, twice as many. Okay, so let's say instead of this, let me say this is 10, right? So twice as many girls go sailing as they go climbing. So there has to be twice as many. So more go sailing than they do climbing. Twice as many, double. So how many go climbing? 10, 15. So sailing has to be more than that because twice as many. So how many times more? 2 times more. So it should be 30 altogether, which makes this 25 because the entire thing represents sailing. So it could come up with Venn diagrams, could come up in different situations. So you need to be able to convert the literal statements into equations. Now, what would be the equation here? It would be let's see, twice as many girls go sailing as go climbing. So let's say we have C and S. So twice as many go sailing as they go climbing. So if there was C, 10 people go climbing, then 20, 2 times of that, 2 times of the amount that go climbing go sailing, right? 2C equals S. Okay? Next, the average time for Tony to mark one question B is 2 minutes, more than the average time for Nargis. Okay, so I'm going to say average time for Tony to be T, average time for Nargis to be N. Okay, what am I dealing with here? So average time for Tony to mark one question B is 2 minutes more than for Nargis. Okay, 2 minutes more. Okay, so Tony takes more time, so N plus 2. 2 minutes more than, so here the keyword, I think, more than. 2 minutes more than Nargis, N plus 2. T, Tony takes 2 minutes more than Nargis, right? So I think understanding what operations are involved, is it subtraction, is it addition, is it multiplication, division, you want to get used to it. Yeah, there are plenty of worksheets around this as well, so give it a go. And yeah, so with practice you should be fine. But yeah, page 21, we've got quadratic inequalities. Right, so here I think we're supposed to have a graph like that, right? And yeah, okay, so what do we have here? Right, so if we look at the first one, the clear error is you can't do quadratic inequalities like this. You could use the graphical method or the number line method, the most popular one being the graphical method. So it doesn't work like that. You can't break it down like that, right? So this is not the way to go about it when you're dealing with quadratic inequalities, right? Quadratic graph. The graph looks good. Yes, how do I know it's, does the student know that it's a minimum graph? Well, the coefficient of x squared is positive, so it's a minimum graph, and they've found out the solutions by factorizing. And so they're looking for when this is greater than 0, when the curve is above the x-axis, right? When it's above 0, more than 0. So the range is these two. But what the student has done wrong is trying to combine these two, right? And then done some of this. So here it's sort of saying, kind of saying x is greater than 3. This part is saying that x is less than minus 2. It's sort of saying both of these. But why is it wrong? Because it does not make sense. It's sort of saying x is between 3 and minus 2, which cannot happen. Can a number be greater than 3 and less than minus 2 at the same time? So this is the meaning behind this. This is x is greater than 3 and at the same time is less than minus 2. Give it some thought. Is that possible? Some number to be greater than 3 and at the same time be less than minus 2. Doesn't work, right? The real answer to something like this, how do you want to put this, is x is greater than 3, or you want to mention that it's or x is less than minus 2. So here the option is or, right? Now what if your answer or the quadratic inequality was different like that, which would indicate that this is the region we want? Now here, yes, x is between 3 and greater than minus 2. So this, yes, x is between greater than minus 2 and less than 3. That works. Right? But here there are two separate regions, two different possibilities. Option 1 or option 2 cannot happen at the same time. Right? So that's something to have in mind. So this would be the correct one. This would be completely false. Do not write it like that. You're not going to get your final answer. Page 22. Change the speed of x kilometers per hour into a speed in meters per second. All right. Okay. I think the student here, well, I think maybe I did the workings here. So yeah, I sort of made it look like this could be a typical working, but yeah. So one of the, let's just say, I'm going to fix a few things here. So let's say, so everything looks good. Converting kilometers to meters, multiplying 1,000. Per hour means hours is in the denominator. That's a common way to think about it. And then convert that to seconds, 3,600, and then simplify, right? So the first step looks good, very solid. And okay, so here I sort of added x because this has to be x, 0.27x. But still, this would have been, final answer wouldn't have been given. You don't get A1. Why? Because 1,000 over 3,600, you could simplify that. It'll be 5 over 18. That'll be 0.27, and it'll go on. 0.2777 and on, right? So you've essentially rounded the answer, and now it's not the right answer. That's not exactly what this is, right? That's not exactly what it is. So in simplifying does not mean you need to round your answer and give the answer. So the exact answer that they were expecting was 5/18 of x, right? Or, well, yeah, 5/18 of x would have been the right answer, right? You wouldn't convert it into decimal because you're losing the accuracy. This is not the same as 7. In fact, it's not even the same as that, because that's still not quite exactly the same. So that's why there's a difference, right? Okay, similar problem here. You might see that this error, not just for this question, it's sort of this rounding to lose accuracy can affect a lot of different questions. So here's another one. Working with straight lines, where we classically, so L2, we're trying to rearrange and get it into the form of y equals mx plus c. Nice attempt here, dividing both sides by 6. As we mentioned, I think the first couple of pages, I think we saw that we would do both terms divide by 6. And so you would end up with, so this person has done -2 over 6x plus 1. Again, I think that was the error, or one of the errors at least. It should be 1 over 6, right? Both terms being divided by 2. But even if the student got that correct, still it would have been wrong because they've said y equals, when it should have been -1 over 3x plus 1 over 6. They've rounded this to -0.3, where it's actually -0.3 recurring, right? So technically, they could have written it as -0.3x plus 1 over 6. But this is difficult to work with. You can't really do anything with this, right? It's difficult to work with in certain questions. So I would prefer leaving it as a fraction in its simplest form, right? So keep these things in mind, right? In straight lines, you really need to know and be aware of when you can round it and when you should not do it, right? These were big errors. These may look like they were small errors. These completely lose marks, right? And here you might even not be able to go through the question if you do this, right? You're losing the equation entirely, right? You can't say y equals anymore when you round it. It's not equal, right? So yeah, always maintain accuracy and do not avoid premature rounding. Exactly, avoid premature rounding. Okay, sometimes you can go too far about this idea and then write all those digits. That's also not necessary because now it's 2025. You have calculators with all these features. You can save your answer, especially if if there's not a lot of intermediate steps. Like in your IGCSEs, you're not going to have so many different steps where you're going to be using the answer over and over again. So you can just write 14.13 or 137. I would prefer writing it as 4SF, right? But then maintain the answer in your calculator with the answer key. It'll be, the last answer will be saved. Use that in the next step, right? So write your answer like that, right? And then go ahead in your calculator itself, right? Because what happens, this is not a bad thing, but what happens is when you read this, and when you again, the next time second time you enter it in the calculator, you miss out one of the digits. 3 becomes 7, you sort of swap them, or you miss out one of the digits when you're typing it in the calculator back again, because you didn't save it, right? You rather want to inspect from the what you wrote here and write it back in the calculator, right? You can get into error, and that's what happened here, right? All the method was correct, but the answer was wrong, right? There was a small error, some digit wrong, because it was entered incorrectly in the calculator, probably, right? So yeah, avoid that. You don't have to write all these lengthy digits. Write about 4 significant figures. Use the 3 dots, ellipses, but maintain your answer in the calculator history, and then use that, right? So I have sort of mentioned certain practices that you must follow, right? So I'm doing this webinar in as early as now, 3 months or 4 months ahead of the actual exam, because I want you to get used to these things. All right, and then, so yeah, what I wanted to say is, yeah, from now onwards, practice these good things, good practices. And if you have any bad practices that you are doing so far, use the past papers, those opportunities to actually practice these good practices and avoid doing these, areas, avoid misconceptions, avoid these little things, and try to fix these things and make it natural to you, right? You shouldn't force yourself at the exam to, okay, I will do this in the exam. I will make sure that I won't round it prematurely. I won't, you might tell yourself at the exam, I'll do it correctly, but for now, I'll just do it the way I feel like it. But no, when you're doing your past papers, the purpose of the past papers is not just getting used to the questions, right? Part of it is to practice, to identify where you can go wrong, where you can lose marks, where you can gain marks easily, right? And where you can go wrong, right? Where you can sort of make errors under pressure. So you need to put yourself under exam conditions. What I mean by that is with timing, right? With being precise about your workings, right? You want to pay attention like it's the final exam, right? So you want to put yourself under pressure, and you want to be as accurate as possible when you're working it out. Even a simple question, take it seriously and show your workings, be neat, and yeah. And be very strict with, if you're marking it yourself, be very strict, right? With your marking. Penalize yourself for what you've done wrong. It could be with single digit, penalize yourself, look at what marks you got, right? Do not try to reward yourself for the errors that you make. Penalize yourself, see if you can fix it before the exam, ideally, right? Okay. So here's a good practice over here. This is very nice. So conserved the accuracy, instead of simplifying it, left it in terms of pi, because that's not what they expect, right? So he'll be using this directly over here. So 100% accuracy is transferred. Accuracy, preserved, accuracy. This is perfect. And then finally got the answer and then rounded it to the amount of significant figures they wanted to, 3SF, right? Perfect. That's exactly what you want to do. Okay. Right. Before we did that. All right. I think it's time we sort of wrap up. I feel like we had a long session. I've sort of feel like I've sort of covered what I wanted to cover. Um, yeah. So yeah, for those who are watching the recorded video, I'll add the website where you can find old archive exams, which you'll find really good questions, and will be useful for tackling questions that are from that are new, right? The new syllabus. So do not just ignore them. I see some really nice questions that test deeper understanding in old questions. Um, right. And if you have any questions, you can reach out via WhatsApp. You can email us. We offer one-to-one sessions to help you get a good grade. And yeah, hopefully we'll also arrange another webinar to cover some difficult topic. Maybe that'll be uh, more targeted toward a particular topic. This one was more, broad, trying to cover common errors, how you can fix them, what you should avoid. So yeah, see you from another video or webinar or live session from Cloud10X. Until then, yeah, see you.